Maybe we can get started. So thanks very much for coming, everyone. I'd just like to start by acknowledging the first Australians on whose traditional lands we're meeting and pay our respects to the elders past and present. And today we have Professor Ryan Fogt from Ohio University, whose research in climate dynamics has been sort of focused on large-scale atmospheric circulation and their effects in the Southern Ocean, Southern Hemisphere, and especially Antarctica. So today he's going to be talking about sea ice. And I'll let you take it away. Thanks.
Great.
Thanks very much.
Yeah, thank you, Will, and thank you, Nerly, for having me. It's great to be here. I must say my sampling of Australia is very limited to just Melbourne and here. And so it's really great to see more of the country and the capital. This is work that I've been doing for quite a while now with sea ice reconstructions. You can see lots of collaborators on the screen there. And also like to acknowledge several students that have been working on this. Amanda, during the pandemic, helped produce these reconstructions originally in 2020. Ashley has done some work with the endurance expedition that I'll show at the end. And Nico's doing work right now with me as a master's student, updating these reconstructions to the present time. Okay, so we'll talk about these station-based seasonal reconstructions here. I'm going to provide a little bit of background and overview. So that title slide here had this MODIS image pieced together of Antarctic satellite composite. And if you're keen at looking at these things, you probably can see the sea ice underneath the clouds. It's a very stormy, active region the Southern Ocean is, but the sea ice is overlaying like this. And this is from October of 2023 when the sea ice was reaching a pretty weird state, well below normal at that time of the year. And if you look at the sea ice by itself here, you can see the yellow line now more clearly. That's the median extent from satellite observations. And there's many places where the sea ice is quite below that. But there are places, as Channing mentioned this morning, where the sea ice is actually a bit above that. A really interesting year, 2023, and that'll be a kind of the focus of many of the things that I'll be talking about with you today. So first we'll look at the change that satellite observations provide us here, and what can we learn from what's happening with sea ice from the really good record, but relatively short record of satellite measurements. So if you're not familiar with sea ice annual cycle, it's really quite large in the Antarctic. It basically can grow as large as it wants to, north where there's not a barrier to stop it. And so as long as it's cold enough to support the growth of ice, it can do so. But it does the growth quite slowly compared to the decline, which happens much more rapidly starting around October. This is the annual seasonal cycle here from satellite observations, kind of the normal range of sea ice observations. I want to focus on a few years in particular outside of this. So this is the year 2016 in blue. This is the year when things started getting interesting. What happened in this year here is that sea ice peaks pretty early on. Normally it reaches its maximum in late September. In 2016, it reached its maximum right at the end of August. There were some strong storms that came through and evacuated ice away from the edges and had a decline and then kind of leveled off and then began its normal decline in October. But that kind of early conditioning of a maximum preconditioned the ice to be in a low state for the rest of the year. That fed into the 2017 year when sea ice hit its first record low in recent times. It rebounded only a little bit, but it was really quite below average for that whole year. And then we went to a period where sea ice had a slow but steady growth back to normal. And in 2021, after kind of being in a normal state for about almost a year while we're in the pandemic, sea ice did this thing again, where it had a really early peak, or actually a record peak, again in late August, and then started a rather slower decline throughout the rest of that winter into spring. And then once the sun came back up and over the ice and led to the rapid decline later in the year, preconditioned to have a really low state throughout the rest of that spring into the summer, and led to another record year in 2022. Then in 2022, it stayed below normal throughout the whole year this time. It didn't have that kind of weird peak in August and declined rapidly again, which conditioned it to have this really, really weird year in 2023, where now it was below normal for quite a bit. And in the winter, very much below normal. Depending on how you measure this, it could be 3 to 6 standard deviations outside the range of normal variability for winter sea ice. I put a frown face here because these sea ice conditions are not just interesting for scientists, but they're affecting ecosystems and lots of other things in a very negative way. So there's not, even though it's really exciting as a scientist, there's a lot of consequences of low sea ice years. If you want to bring it up to more modern times here, 2024 was really low as well, but it wasn't as alarming as 2023. There were a few daily records that were set in 2024. What's interesting about this year in particular is at the end of 2024, it kind of went back into normal space for a little bit, the end of summer or end of December, and stayed that way for the beginning of 2025, but then progressed now down to a really low year again. It won't probably be a record low. It's still too early to say for sure, but it's within the 2023 record low right now. This is a kind of fun animation that shows some of these things in longer context. So with all the years together, the first few decades of the sea ice was kind of in the noise. Then we had this persistent years of relatively higher sea ice concentration and extent, followed by record low years. This only goes through 2023, but you can see as it's tracing that line here, how anomalous that year was compared to the rest of the satellite observations, in particular as it gets to the winter season there and its maximum, really how different that 1 year was from the norm. You can also see this. These are some images that Channing was also showing this morning. I love these presentations from Zach because the contrast is so sharp. But the yellow line there at the bottom that stands out is very different from the rest. It's 2023, 2025 started out normal and kind of is emerging now towards that 2023 minimum, but it probably won't cross it. And then this time series here, which just shows that steady kind of and weekly, but statistically significant increase up until around 2015, that sharp decline into 2017, and then relatively below normal. It did go above normal for a bit in 2021, but stayed below normal really much of that last 5 years. You can look at this and also in the minimum timing. So when the sea ice reaches its minimum throughout the year, what's the value of that? There's been a decline in that after a period of growth, 2023 being the lowest one on record, and also at the maximum. This is probably easier to see because there's a little bit less interannual variability, and where you see that upward trend up until about 2014, and then decline after, and then in particular, how low 2023, the last mark on this graph here, is compared to those other years. It just stands out as something quite different than the rest. Very, very different than what's going on in the Arctic, right? The Arctic is showing a weaker recently, but certainly a long-term decline that's consistent with global climate change and changes in rate of forcing in that region. But the Antarctic is doing something quite different. The challenge with these observations, though, is they're based on satellites, which start around 1979 for the whole of Antarctica, meaning that we may not resolve fully decadal scale variability. We only have a bit of the picture of what's going on in a very complex system. And so what we're doing, what we want to know is like what happened to sea ice before these satellite observations. And so my team at Ohio University here has been working on this for quite a while. We've been doing lots of different climate-based reconstructions of Antarctic climate, pressure, the SAM index, but most recently sea ice. And so we're trying to place these in a longer-term context by looking at reconstructions throughout the 20th century. These are statistically based, controlled by observations of climate in the mid-latitudes of the Southern Hemisphere, not paleo proxies, but looking at relationships that are existing in the natural world between Antarctica and the rest of the Southern Hemisphere. So these reconstructions were published in 2022 in Nature Climate Change, and I'm happy to share that paper with you if you haven't got access to it yet. I'm going to spend a little bit of time talking about what we did in this, and then a lot of new things that we've done since this paper has come out. So we reconstructed sea ice based on 5 different sectors for seasonal means. So you can see these sectors over here on the right. These sectors were defined by Raphael and Hobbs, basically on the graph on the left, when the red line kind of has a dip. That says that longitude is kind of a boundary where that sea ice region is behaving a little bit differently than the regions beside it or around the rest of the continent. And so it allows us to look at these sectors somewhat separately. And so we have a time series for sea ice extent in each of those 5. We also reconstructed.
Sorry, Ryan, what is the red line?
It's the decorrelation length scale, spatial decorrelation length scale. So like how well is that longitude related to the longitudes nearby? Yeah, so we did those 5 sectors, and then we also did total sea ice extent 2 different ways. We did it as one index, one time series. That's hard to do for us because our methods, as I'll mention in a bit, don't really work for the complexity that's happening. That's more manifested in the regional locations. But then we also did it as a sum of each of these 5 sectors, adding them up together like you do in the region. All right, so I mentioned that these aren't based on paleo data, but really just station data. So we have 30 different stations that have really good long-term continuous measurements from the beginning of the 20th century. I've spent a lot of work over the years trying to homogenize these points because stations move, they change sensors, they change reporting times, different things like this. And so we have now 30 good homogenized records, including many here in Australia and New Zealand, that serve as predictors. And we use temperature and pressure measurements from these stations to relate them to the 5 different sea ice sectors that you see there and develop a statistical model to understand how these measurements can relate to sea ice around the Antarctic continent. This is the methodology. I'm not going to go into a lot of detail. Basically, we do 2 different processes. We do a data reduction technique so that we don't have to worry about all of these 30 stations individually, but rather more the relationships they share with each other and the relationships they share with the Antarctic sea ice. Once we have those kind of data reduced down, we then do a multiple linear regression to relate those shared common features of the observations with the sea ice in the regression model. And so this kind of is all ultimately working to remove any kind of unrelated noise that's going on in the weather and climate in the Southern Hemisphere that's not related to the sea ice. We use lots of different combinations to get ensembles. So we're not just doing one model. We do various configurations of these stations to give us a spread of different outcomes of past sea ice as well. And then on top of this, we layered the climate modes that we know influence sea ice as well. Things like the southern annular mode, all these ocean circulations that you're all very familiar with here in Australia, that also influence, at least regionally, the Antarctic sea ice extent as well. And so when we layer these on, along with the station observations, we develop an ensemble that has up to 41 different reconstructions for each season and each sector. The box plots I'm showing here are skill metrics from this reconstruction. When you sum up across the 6 sectors, there's about 244 potentially unique reconstructions. You can see the number of ensemble members in the plots. We don't quite get that many because we don't use all of the different climate modes. They're not always related. This is for all sectors in the blue, and then the best fit reconstructions there in the red. And there's 4 different skill metrics that are shown here in the different boxes. I'll go through them because I'm going to use them again later. Cal-R is the calibration correlation. This is the easiest one to get right. It's basically the correlation of our reconstruction with the direct sea ice observations. We expect that to be pretty high because we're calibrating the model to get that as high as possible. RE, reduction of error, measures how we're doing performing compared to the climatological average. So during the calibration period, and anything above 0 means that we're adding more knowledge than the climatological average. This is done in the calibration series. That should also be a pretty high statistic. The ones that are a little harder to pass are the Val-R and CE at the bottom here. Val-R, we create a separate independent reconstruction by predicting 1 year at a time, independent of all the other years, and then merge all those predicted years into one continuous time series, which we call our validation time series. And so that one's predicted values all throughout the time. And then we correlate it with the observations, and that gives us the validation correlation. And then we do a similar test to compare that reconstruction to the climatological average to get the CE. So the CE is probably the hardest to pass. Anything, again, above 0 here indicates that we're outperforming the climatological average, which is not a very good base mark, but really climate models that go back into the beginning of the 20th century just use the climatological average sea ice. And so we'll provide you more information, at least, even if it's a low benchmark to kind of aim at. You can see all of these metrics are well above that. 1, by the way, is perfect. If it's at 1, it lines exactly. Every little point, every little variation is perfect with the observed. And so you can see we do have pretty good skill at doing this method. All right, so our paper highlighted, we used the word regime shift in that paper before it became a thing. It's now all you hear about Antarctic sea ice. We're talking not about the current regime shift in this paper. This kind of predates that. We're looking at a 20th century regime shift and that we saw manifested in 2 different ways, trends and also variability, which now is becoming the story. So,
Ryan, can I ask you a question on the model? Like, what variables do you input are the most sensitive? Or I guess, like, you know, do you have some sense of like which inputs have a larger control over the skill?
It really varies by season and sector. There's not one that's always like everything is so Australia and New Zealand have a lot of influence actually because of the teleconnections that exist from those latitudes down to the sea ice, especially when you're looking at reconstructions in the Ross all the way to the Weddell Sea. When you get to East Antarctica, it's more like things that are going to give you zonal pressure gradients in the SAM. So it's pretty even actually. So it does depend on season and sector. There's not one bullet point. All right, so this is our total sea ice extent reconstructions. The black is the observation, the blue is our reconstruction, the gray is an uncertainty envelope. I can go into how that's calculated, but it's basically where we think with a 95% confidence the sea ice extent would actually lie. These are for the total sea ice extent. So this is done by both the reconstruction to the total sea ice time series, which is the black, but also the sectors added up. And so the gray actually includes almost 1 million different ensemble members. It's a lot of different, well, several 100,000 ensemble members when you add up all those different configurations of the sectors. And what we saw in this is what we call the regime shift, that if you look at the non-summer seasons, there has been a marked decline in sea ice extent in our reconstruction across the ensemble mean through the early 20th century to the mid 20th century. And then the observations start and it goes upward. And so this suggests a couple things, that the observations started ubiquitously or randomly, I guess, in a period of relatively low sea ice extent throughout the 20th century, and then had this upward trend. And so our idea of regime shift was this persistent decline that was seen in most seasons throughout the early 20th century that then flipped during the period of satellite observations to this upward trend. The other thing we talked about in the paper was this concept of changes in the variance and variability. And you can see that really clearly in all seasons. I'm just highlighting it here in the summer. Really big decline from a record maximum in 2014 to a decline in the record minimums that I talked about first in 2017. These reconstructions were in the paper ended in 2020, so they didn't get the events most recently. I'll talk about those later on though. We looked at that a little bit further in the paper, and we noticed here in the PDF the distribution of different anomalies of multi-year changes. So looking at 2-year averages consecutively and how the sea ice shifted. Normally it doesn't shift a whole lot, and you can see that in the black observations here. They're centered around 0, our reconstructions in red and blue. But you'll see these really big lost years here. That's from the record min to the record max. Sorry, the record max to the record min. So 2014, 2015 average jumping down to the really low values in 2016 and 2017. Those fall outside of the range of most of our reconstruction ensemble members. So something was probably happening. We're getting an idea on our reconstruction that there's something unique going on right now in sea ice that our reconstructions don't capture the full magnitude of. Okay, so more recent work since that paper. First thing you want to know, how unique are these current extremes in the context of the 20th century? We touched on it a little bit in the paper, but since that paper has been published, we've done a lot more work as more and more records have happened and more extreme sea ice years have happened. This is a figure that I didn't actually make, but was made by colleagues at the NSIDC in the US. They, by the way, host my reconstructions, so you can go on the NSIDC and download them there. They have a great user's guide and everything about all the different ways that they're done and the uncertainties and so on and so forth. They used them and made this graphic when 2023 sea ice year was going on and said 2023 is off the charts from this reconstruction. And so this shows you the uncertainty envelope there in the gray lines, but then how low that 2023 value is over here. It's just much, much different than anything we've seen in the reconstruction.
Ryan?
Yes, sir.
So if you look at the 2017 to 2019 years, your reconstruction is significantly higher than maybe not statistically significantly, but it is higher than the actual observed.
Yes.
Have you run your reconstruction for longer to see if you get the minimum extreme in 23?
I will talk about that later.
Oh,
Yes,
sorry.
absolutely. Good question. Yeah.
Oh, wait.
Yeah.
Okay.
Yeah, absolutely. So yeah, our reconstruction ended in 2020. You can see that these values, even the observations when we're calibrating, are right at the edge of our uncertainty envelope, sometimes falling just outside of it. So even before that, 2023 year hit, we were kind of at the fringe of what we're predicting. We delve into this a lot more. So we have, with our ensemble approach, lots of different configurations of winter sea ice. So I'm going to show you what's happening here. This is the total sea ice extent, and then I'll break it down into sectors in a bit. So these are observations from satellites. At the top is the value of the sea ice extent, seasonally average for those 4 seasons in millions of square kilometers. And then on the bottom, the number of observations that fell below the 2023 value. It was a record in all 4 seasons for total sea ice. We add our reconstructions on here. Don't worry about the fitting statistics at the top. What you can draw your attention to here is the number of ensemble members that fell below 2023. And you can see the ensembles perhaps on the screen as gray lines. And so in winter and in spring, the bottom 2 panels, none of our ensemble members had a value as low as 2023. In this is when we're actually calibrating and fitting to the total sea ice extent time series. So we have a smaller ensemble. We only have like 9 or 6 different ensemble members here. But when we now break it into adding all the sectors, which have some 40 maybe ensembles, and all the permutations, configurations, we can approach over 1 million different ensembles. So you can see here, 2 million. This one here in winter, we have 134 million different configurations of winter sea ice anomalies. And so this ensemble range includes all of those for the 4 different seasons. This 3 sigmas in green, the ensemble mean in blue, and then the observed values from 2017, 2022, and 23 are different colors on this. And what I want to focus on here is the winter one, because that's where things were getting the most extreme. It's within 3 sigma of our ensembles, but if you break down the percentile ranks here, it's really low. And if you counted, we only have 72 out of 134 million winter sea ice values that are as low as what happened in 2023. Now, this could mean 2 things. The first and probably simplest explanation is that the reconstructions are complete rubbish. And I'm humble enough to admit that's a possible thing. All reconstructions have uncertainties. There's limitations to these methods and assumptions that you have to make. Maybe they're not valid. But I think the answer, like everything for Antarctica, is much more complex than that. And that's where I think it matters when you look at things regionally. And so going back to this figure that also Channing showed earlier this morning, regionality matters. Not everywhere in 2023 was sea ice below average, even in the heart of winter, like in this one day in July. And so when you look at this by sector, you can see that we actually do a pretty good job of representing uniqueness in regions where it was and was not unique. And so going over here in the Amundsen and to the Ross Sea, none of the observations in the Weddell were ever that below, but it wasn't a record at all in the Amundsen Sea. It wasn't a record in the Ross Sea, and our reconstruction ensembles have much higher probability of these events happening in those sectors. When you move over here to East Antarctica, it's a record in the observations. None of our ensembles capture that. We have a fluke here. There's probably a bad reconstruction. So we do have 2 ensemble members here out of 812 possible ways of looking at the winter sea ice there that do get as low as that. But those ones look a lot different than the rest of the pack. So we do have some of the regional signals, which makes me think there's something going on more specific. I will point out, yes.
This feels like an extremely naive question, but would you have expected to see that same pattern of decrease to 1980 and then the increase that you see in the total extent somewhere in these? Or not so much?
Yes, we did. I mean, we looked at the season in the paper actually specifically, and so the way I'm projecting them here, because I have a lot more text on the slide, makes it hard to see. But there is a decline in some sectors. So like we saw it in this one here and in the Ross sector in particular.
Is there? It's just you can't see it.
It's squished, yeah, and so it's hard to see in this projection, but it's hard to see actually the upward trends as well because it's compressed. Because I had a lot more text here, but there were certain sectors that showed that decline more than others. Or that regime shift, or whatever you want to call it. I want to mention too that CMIT6 models don't do this very well either. These extremes. It could be the models aren't great. There's a lot of issues with sea ice in the models, but this is a paper that was published by some colleagues in the British survey largely that showed that when they do happen, it takes a long time to recover. The ones that do recover from these sorts of long, persistent, really extreme anomalies typically have really large interannual variability that seems unrealistic compared to satellite observations. So models themselves struggle to, and they have large ensembles as well, some of them struggle to capture quite a bit of this extreme state. So it begs the question, why such an extreme anomaly? This is not stuff that I'm working on, but a lot of people a lot smarter than me have. Will Hobbs and colleagues published this paper, used the word regime shift, and this is a slide that I've stolen from Phil Reed in the Australian Bureau of Meteorology here. Basically, in the paper, it says that in the satellite observations, there seems to be a strong role of the atmosphere for much of it, but the recent changes cannot be explained by the atmosphere alone, and there's support that the increased variance in these really low extremes are suggesting a change that's happening in the sea ice system, moving away from an atmosphere-driven sort of regime to one that perhaps is a stronger oceanic influence. And this is followed up by a paper that you also showed this morning, Channing, that shows the ocean timing of sea ice anomalies is also quite consistent with the changes in sea ice, heat being vected upward in the ocean, leading to a warmer surface condition in the ocean that could be consistent with the melting and reductions of sea ice in the recent years. So perhaps an ocean influence as well. A lot more work needs to be done on that. It's really complex. One thing that I did with a group of people that reproduced my reconstruction method using Antarctic data. So it goes back to 1957 only, but it includes all of the Antarctic observations as well as subantarctic islands. Published another reconstruction. And in that reconstruction, they found that there was a similar drop at the end of the 1970s, not as large in magnitude as the one observed, but another one that happened. With this detail that the spatial footprint of it looked very similar in that reconstruction. This is, by the way, done in a model. So they can look at multiple fields, not just sea ice, but the temperature and circulation as well. And they found that there's a strong change in the ocean that's providing the memory that amplifies the magnitude of both of these drops, the most recent one and this one that happened in the reconstruction in the late 1970s. So that's the reconstruction of them in the red. My original one is in blue. We're not comparing apples to apples, even though it looks like we are. I didn't produce annual mean reconstructions, so we had to kind of do some weird seasonal averaging to get an annual mean, and I didn't include any Antarctic data. So, but nonetheless, we have a lot of similar variability, which is encouraging, even if I don't have the same magnitude of the drop in the 1970s as they do in the red. So here's that first drop. And it's similar, although it's subdued in their reconstruction compared to observations, both for mine and for theirs here. And this is, by the way, total. The paper goes into some of the different sectors and looks at that relationship there.
Ryan, the Antarctic data, that's still atmospheric data that's being brought in. Yeah, so it's all
Temperature and pressure. That's right.
Yeah.
Yeah. Okay. Some other work that we've been looking at goes into your question here. What about the recent values? And so we did this in two different ways. The first was, let's just extend the model to calibrate it from the beginning of satellite observations, including 2023. I have not done through 2024. It takes a lot of time to go through all the observations and get them in the right form. So I've only updated them to 2023, but that does include all those really weird anomalies that happened throughout that year. And so first I'm showing you the skill statistics. The original ones that I published are in red. The updated ones through 2023 are in blue. And now I'm showing you individual ensemble members as outliers with dots. The skill declines. It's not as good as it was when we didn't have these extreme events, which you might expect. But overall, it's still quite a bit above, especially like the IQR, the interquartile range. It's well above this 0 benchmark for all seasons and all sectors. So that's encouraging. So when we do calibrate with that recent period, we do capture quite a bit of that extent. And I'll show you that here. This is plots from my graduate student. So I apologize that when I stole the figure from his thesis, that the label bar didn't match up very well. So the black is the ensemble mean, the purple is the observations, and the blue dashed is our 95% confidence interval. And so you'll see that we do have a drop in the winter where the drop happens the most. We have the drop, but the observed falls within our confidence interval. We've calibrated to hopefully capture that, but it's right at the very, very edge, right? So it's not capturing by any chance the magnitude of that drop. What's interesting is that the maximum that we captured before, when we calibrate to 2023, that includes this really low value, is not captured as well. And so we're fitting here, capturing different extremes that you don't capture all of them. But even in the spring here, when we calibrate, we capture that drop. This is for the total. We do much better in the Liddell Sea than any other sector because there's more data, and it's closer to South America and other predictor stations. And so we actually do produce the magnitude of those drops very, very well in the Liddell sector. A more challenging question, and probably the better question to ask, is when we don't calibrate, we just extend, how do we deal? So this is using the original reconstruction model that we did for 2020. And each station or each predictor variable has a weight that we can use, and we can update the variables and then use those weights from the original model to try and predict the recent effects. This is probably the better way to go, so we're not training it on any of these recent extremes. How well do we do?
Wait, sorry, Ryan, can I ask one question again?
Yeah.
So what are the ocean-based inputs into the model again? Because if the station data is mostly atmospheric and this work from our end is suggesting that the ocean is potentially important in explaining recent changes, then might you expect that a statistical model based mainly on atmospheric measurements might not?
Absolutely.
Yeah.
Yeah, and so that's what we're testing essentially. We try to indirectly account for the effect of the ocean by using a lagged effect. So we allow these predictor stations to lead the sea ice extent anomalies by up to a season for the slower time scales of the ocean, but also for the sea ice itself. So we indirectly count for it, but we do not have any long-term continuous measurements of ocean other than like INSO and IPO and those sorts of tropical or global modes. We don't have any in situ long-term records of ocean. We don't even have very good ones now over the satellite era. So yes, our thought is if it doesn't do so well, that there's an ocean influence that's coming out. And so that total drop in the winter, where we're at the very edge of the confidence interval, don't capture the magnitude, suggests to me that perhaps the ocean is playing a much more important role. And a model calibrated to primarily atmospheric processes is not able to capture that extreme. Absolutely. And you'll see that emerge here even more when we start to do this for predicting the recent values. So I'm using a stoplight approach here. Red means that the values, when we predict them, do not fall in the confidence interval. The green do. And it's interesting, it's a regional and temporal match. So 2021, when things were pretty normal, we do pretty well, almost everywhere, including the total sea ice extent. In 2022 and 2023, it's mixed. For 2022, these areas where it's not a record, overall, we tend to capture, except for the winter, those areas, we still don't capture the full magnitude of those. And then in areas where it becomes a record and really extreme, East Antarctica and King Haakon, that's another sector east of the peninsula, the Weddell Sea, we don't capture. And the total, when you add these things up, we don't capture these recent extremes. They're just much, much lower than our model does, suggesting again that the atmosphere is probably playing a less role in these processes. I'll show you the time series of these. These are produced by my grad students. So the white is the observations. If you see the white, it's the bottommost layer that's graphed here. So if you see the white, it means that it's probably not being captured very well in the reconstruction. The dashed line at the very, very end here is our updated, predicted, not calibrated. So we just use the weights and extend the reconstruction forward. This is for the Amundsen Sea where we do well. All right. We capture almost all of the extremes throughout the full time period, including what happened in the recent years. They weren't records. They were kind of in the same sort of patterns, suggesting that there's a strong atmospheric wind-driven circulation still going on in these regions that maybe is not being overcome yet by the ocean roll. The Weddell Sea, we also do very well. And so predicting these recent values, they're really close to what our reconstruction would indicate. When we start moving east of the Weddell Sea, things fall apart quite a bit. King Haakon, you can see that we're not close. In some cases, we have the model going slightly up or steady and it's declining. Here in the winter, pretty high, very low. And so in certain sectors in these most recent years, particularly as you move to where we think, based on that paper I was with Fogt, where the ocean might be playing more of a role, we're not capturing those extremes very, very well. And East Antarctica, same story. Actually, in all 4 seasons here, the sea ice extent in recent years is doing something different than our reconstruction is indicating. Okay, and then total, no surprise, when we add them all up, overall, even though we're getting it right in a couple sectors, we're not getting it right in enough of them where the changes are large enough to capture that anomaly recently. Okay, last bit here I'll talk about is some fun work that an undergraduate student of mine, Ashley, had been working on for an honors thesis for an undergrad to look at another way that we can use these reconstructions to place interesting historical events in a longer historical a better context. And so we looked at the Imperial Transantarctic Expedition of 1914 to 1917. This was brought to our minds recently because if you hadn't heard the news, in 2021, they found the Endurance at the bottom of the Weddell Sea. It was really kind of exciting news. And so we're thinking, oh, what can we say about why did it sink? We know why it sunk. I mean, it got crushed. But what was it, bad luck, or was there something going on that year? We had done this before with the expedition to the South Pole, by the way. We looked at the race from Amundsen and Scott and found that, you know, the weather actually conditions favored Amundsen more than Scott, and just based on where they were and just impression of constructions of that race. It's a really fun story. We found another really interesting story that emerged from this comparison with the reconstructions. A bit of background, if you're not familiar with this, it's probably one of the most famous pieces of Antarctic history. Shackleton led this expedition. There were two groups. I'm going to be focusing on the Weddell Sea party. What I've plotted here are the locations of the party, mostly on the ship, but then abandoned the ship later on, and then were on the ice itself. Their goal was to sail as far south as possible, land on the continent, traverse to the South Pole, and then somehow magically rendezvous with a group that was coming from the Ross Sea up to the South Pole. It's even today, it seems ambitious. I can imagine with the instrumentation they had at the time is a very ambitious goal. And no one had ever traversed at that time from the Weddell Sea up to the South Pole. And so they wanted to be the first to make that kind of crossing. Well, as you know, hopefully this story changed really quickly. They come down into the ice, they get stuck into pack ice really quickly, within a couple of weeks actually of sailing out of South Orkney Islands, and get trapped, and then are at the fate of the ice moving around. I'm only going to show one part of what we've been working on because of time, but what we found was that the question we were asking was the destiny of this ship, Endurance, sealed before it voyaged into the sea. In other words, was it just a bad year that they chose? And it would have been different if they had chosen a different year. I mean, was there any chance of success given what happened with the weather that year? And we found that, yes, in fact, it was just a really bad year. So what first started out was a really, really cold start. And they mentioned this in their diaries, of course. But when we start comparing with different climatologies in our sea ice reconstructions, we see that this year was an abundant year of sea ice with very cold conditions. All right, so I'm going to show you a few plots from this work that Ashley's done. So the blue are the observations from the Endurance. We've daily averaged the points. Usually there's 3 or 5 measurements a day, depending on what the weather is like and different things. So those are the blue. What I'm showing you here is temperature. The green is the average along the track that I showed you previously for Endurance or the field party. And those are from a long-term climatology from 1991 to 2021. And then the mean and max from different periods, depending on how much you trust the reanalysis, in red, the purple and the yellow colors. And you can see they encountered pack ice, very heavy ice right off the bat, and became stuck about a month later. And what you'll notice for the temperature here is very cold conditions, near record cold for Era 5 reanalysis along that track. There was a very, very strong storm that happened here that warmed it up quickly for a bit, near normal, and then back quickly to below normal. That storm kind of caused them to get stuck. And unfortunately, because it became very, very cold afterwards, once they were stuck, they weren't getting out that late summer into early fall. The weather was kind of normal. It varied a lot, of course, throughout the rest of the time. The paper looks at the breakup time and finds that there was no hope of an early breakup, unfortunately, either. So that was a second part of the story. But focusing on this abundant sea ice bit here in the cold that happened initially, this is from satellite observations. The green here is the concentration average. I don't have, the Endurance didn't make measurements of the satellite or the sea ice concentration. They mentioned, you know, it was loose ice or pack ice and those kinds of conditions, but it's really hard to get a percent of ice coverage from that. So we're comparing with satellite data here. Moving in, early on, they encountered pack ice well above normal for that region. So you can see they encountered pack ice when sea ice was not normally above 80%. In fact, in the satellite observations, it never had reached 80% at that location. When they became stuck on the ice, even at that point, the normal, it really increases quickly afterwards, but the climatology for that region shows that they shouldn't have been stuck. Normally, it's in 50 to 60% coverage at that location and time of year. As they drifted farther south, yes, it increases quite a bit, but they shouldn't have gotten stuck that early. Normally in satellite observations, it wouldn't have happened that way. These are very short, so we use our reconstructions to understand them a bit more in detail. We do a great job of reconstructing the sea ice in the Liddell. That's even true if we predict recent values. And 1915 was the year they got stuck. And you can see in the summer, it's in the top 25% of highest years, the sea ice concentration or sea ice extent there. In the winter, when they were stuck, it was the highest ever in that particular year. And the neighboring years, not bad at all. 1914, 1916, which you see here, had lower quartile sea ice in that year. There's also a fun record from the South Orkney Island of the fast ice, when the ice basically comes up to the South Orkney Islands and stays there. And that's been an observed record from the beginning of the 20th century. So not a reconstruction, but actual observations. And that supports this idea of this really being a really bad sea ice year. Here's the formation. This is a calendar day. So low value means that sea ice is forming or getting stuck at South Orkney Islands early in the year. And 1915 was in the lower quartile for that. The breakout, when it actually left the South Orkney Islands, was in the top 25%, making that year 1915 in the upper quartile of the longest sea ice duration at the South Orkney. And so and this is like 100-year observations as well. So a really bad year for the ship to sail, unfortunately, that, kind of led it to get stuck. And then the conditions never became right for it to get unstuck. Okay, brilliant. Hopefully you understood some of that. I'm happy to answer lots of questions. I have plenty of time to do that. What we've done here is try to produce reconstructions as estimates of what could have happened to sea ice. Based on those reconstructions, and a lot of evidence here going back, suggesting that this 2023 winter anomaly was really, really rare and unique. Similar drops may have occurred before, but those drops still had an ocean influence. And so what we're suggesting is that there is an ocean influence that's happening in these recent extremes, but it's regional. When you're looking around West Antarctica and the Ross Sea, Amundsen Sea, and Bellingshausen Sea, we predict those pretty well, and suggesting there's still a strong role of atmospheric variability, and recent records weren't even broken in those areas as well. And then this fun bit of history here that this endurance expedition, had a bad year and kind of run into really heavy ice and really cold conditions that kind of make it stand out in the last 100 years too. All right, thank you. Cool.
Thanks very much, Ryan. So yeah, really nice story. So can I open up for questions? Are there any questions on Zoom?
I'm sorry if I don't understand the method correctly. If the regime shifts also keeping in 2016, it makes sense to recalibrate your reconstructions after that instead of after the 2020, or?
We want to have as long of a window as possible to calibrate over. My graduate student's been doing separate work that I didn't have time to show, where we've broken the calibration windows into 30 years and predicted 15 other years. So 30 continuous years of data and then predicting them. And it depends on when you calibrate, how well you predict. Basically, if you calibrate in the early period, you don't predict the extremes very well. But if you calibrate over the later one, you do okay in predicting some of the earlier ones. So there is a sensitivity that suggests a time of evolution of different processes coming into play in the sea ice variability, especially for these recent extremes. But we haven't done a calibration from 2016 onward, just because it's very short and very noisy, and we probably would have a rubbish bit of that. It's just not long enough to get enough information in this fairly simple model to reconstruct that very well. Yeah.
Yeah, super cool, thanks. I mean, I guess a lot of these, like the sort of non-linearities, influence of the ocean, and that was it. They were problems that paleoclimate world have dealt with for many, many years. So to preface my actual question, sorry, I zoned out for a second. Your ensemble, how exactly is that? How was that created? Like, what did you change?
We changed the configuration of which predictor stations were used.
Okay. Yeah, so all possible variants of those 30 were.
Essentially, we actually filtered first to make sure that they're correlated. They have some relationship.
Yeah.
So we didn't just use random points. We actually did one with all of them, regardless. And then we did subsets of which ones were correlated. And based on how strongly correlated, we did different groupings.
Okay, so there was no like thinking about 2023 was obviously different to anything in a calibration period, but it's possible there was a year before that was similar. There was no combination of stations that predicted 2023 particularly well.
That's a great question. That's something that Nico's been working on my graduate students. And I don't know off the top of my head. I'm set to read that chapter on the flight back over to Auckland. So I can't tell you for sure off the top of my head. I saw early results, but I haven't read the writing of it. But we did look at individual predictors, how they've changed in the calibration periods, and which ones are really strong and stationary. I mentioned like earlier, Australia and New Zealand tends to be a strong region because of the cloud connections that exist from this region down to most of Antarctica, at least the South Pacific sector of Antarctica. And those tend to merge as pretty consistent ones. But I can't remember precisely for the 2023 one, which one stood out.
So that leads very neatly to the second part of my question, which is, I mean, presumably, and I assume your paper goes into this, but I haven't read it, that you would expect some non-linearities in these relationships, but it's essentially a linear model. Did you test any sensitivity to that? And there's some things like the pairwise comparison method is a paleoclimate one that is specifically designed to sort of try to deal with these. You tried that with your grad student?
Yeah, so the grad student is doing that separate calibration window and predicting over a longer period.
With different methods?
No, it's the same method, essentially. But yeah, seeing the sensitivity at least to the time period of calibration and how that influences the predictors that are involved. I will say that my colleagues at UCLA have led a different method altogether using Bayesian sort of modeling of these. So they use the same predictor data, but in a Bayesian model. And that paper just came out this week. So it's in Nature Communications Earth and Environment, looking at, and we find a structural change as well in that sort of, because that one, because it's much more complex statistically, allows you to denote structural change in it. And so we can see that the recent values from 2021 onward are emerging in a different structural change of the way the predictors work together. And yeah, so it's just out this week and a more complex Bayesian modeling than what I'm doing with linear kind of modeling here.
Is that Marilyn?
Marilyn Raphael's paper is lead author now.
Okay.
Yeah.
I was wondering if you can, looking like in more regional sectors. So for example, like if you look in the Weddell Sea, can you reconstruct the Weddell linear, for example, from stations there? And if that's possible, then can you say anything about frequency of such linear events over longer time periods?
Yeah. So I have separate work that's done with reconstructing sea ice extent, sea ice concentration. But the method that's using does not, if it's in the pack ice, it just assumes it's always pack ice. And so it does not allow for polymia. I'm not aware of anything that's done sea ice concentration that's able to see polymia. Unfortunately, it'd be a really great question, right? That one or the modified polymia, like all these different kind of polymia, how they've changed through time is a really important question for oceanography and for like ice dynamics.
I mean, open ocean polymia are formed through like convection in the ocean. So I'm guessing any predictive method that's based on atmospheric station data wouldn't be very good at.
But then they influence air sea fluxes.
Yeah.
So maybe it's afterwards, a lag the other direction.
Yeah, I will say part of the reason I came to visit early is the work I'm moving forward with now is more on data recovery. And so I have an archive from a climate historian about 1 million, actually like 3 million observations from ships, sealing and whaling ships that were in Antarctica and around Antarctica in the early 20th century through the 1960s. It's just a matter of getting those handwritten logs. They've been scanned. That's some of the harder work has been done, but getting the scans into a usable format, and then having a now whole wealth of new observations, including sea ice. They'll talk about qualitative measures of sea ice, pack ice, loose ice, those sorts of things. And so there's going to hopefully be a collaborator on that project when it goes forward. If the US NSF still exists, which is a question mark. Well, not, yeah. So anyways, yeah, there's more work to do with some things where we might be able to see things about Polonia because there's going to be, well, not maybe plenty, but at least more concentration measurements at different points where the ships are.
So the ocean temperature has to play a role in this, surely. And sea ice is pretty thin compared to ocean. So you're really only interested in the top few meters of ocean temperature. There are satellite measurements of sea surface. Can you make use of that over the last few decades or something as an observation data set?
The challenge would be we would need to know how to understand that information back through the whole time period, because the way this method works is that you need the predictor to exist the whole time period. And so if it's even like, Will Hobbs has given me like different measurements of ocean properties around Antarctica, but they're discontinuous in a way that won't work. If a predictor comes and goes often, it would really influence the results. And so, yes, there are great measurements. There's even some early satellite measurements in the 60s, sea ice as well. But yeah, late 60s and 70s, I should say. So great other points of information, but if they're discontinuous throughout the 20th century, we have to find a way to estimate those in order to put them into the model. Makes sense. Yeah, so the ocean influence, when the model falls apart, I think is what we're seeing is where the ocean is playing a much more important role in these sorts of things. Fortuitously, for much of the satellite observations in the Antarctic sea ice, the atmosphere will be processed. At least it related really well. Recently, not so much, and that's what we're seeing.
Yeah.
So could you test it? But I guess just in running your model, but just over sort of the like 1980 onwards, just to see if you include sea surface temperature, do you get those more recent extremes?
Yeah, that's a good point. Yeah.
It might also be that your only future for this sort of work is to adapt to what's happening now and be able to. Absolutely. You're going to have to look ahead to the 20th century and just use 21st century.
Yes. People have done this work in a climate model. So there's been like paleo data assimilation climate models to predict and reconstruct sea ice and other things. So they use paleo information and other bits of information, corals, tree rings, different ice cores, and then with the physics and dynamics of the climate model to kind of get some of those integrated coupled processes. And they have different skills. There's quite a few of those that exist now, but that's been a way to overcome some of the barriers that this relatively simple method doesn't allow.
Just on this topic, I'm not convinced sea surface temperature would be the right variable because, at least my recollection of some of the work that's coming out of Utah about re-emergence of heat in the following season is that it's actually not the temperature in the mixed layer beneath that is most important. For re-emerging back and actually changing sea ice. And I mean, in our global models, which are free running, not data assimilating, but forced by reanalysis atmosphere, we do a pretty good job of sea ice over most of the record until we hit this. So we think our model is quite good. So I don't see your model as being crappy because it can't get that. I think it's a really hard problem to get. But I actually did have a question there, which is related to the regionalization versus the global. And my assumption is that the regionalization has higher variability than the global, because when you have a stronger or weaker Amundsen sea layer, that'll give you more sea ice in one location, but that'll almost be exactly compensated by less sea ice on the other side of the system. So the regionalization is a very good test for atmospheric-driven regional variability, but the circumpolar one is much more sensitive to the ocean.
Yes.
Which is what we find in the big model as well.
Yeah, The total sea ice extent, I'm just trying to do a reconstruction on that, is always worse than any sector. Because the process is so much more regionally, in the atmosphere world, where the atmosphere is playing an important role, and much more regional. So what these predictors that are looking at the atmosphere in the mid-latitudes and southern hemisphere are getting a regional influence. We do better at the total, actually, when we add up the individual sectors that have been reconstructed individually, sum them up to get the total, rather than use the total time series and try to predict that. So, it's just, yeah, lots of regional processes that canceled out that are important in the atmosphere kind of flows away. But when you integrate them, don't do as well. The same thing, actually, we can't do very well in the annual mean, because the annual mean is such a large seasonal cycle on the sea ice that, has the role of the atmosphere, I think, in variations in different sectors. When you average that out over the course of the year, this model doesn't work very good. So, it's hard to compare with paleo proxies that look at annual resolution because we're looking at some different things and looking at the mean state, we're looking at, different parts of the seasonal cycle separately. So it's hard to kind of compare those two.
I'm going back to ask a really statistically idiotic question. But when you projected the model through to 2023, presumably with the data you have through no fault of your own, that is just not very good at predicting whatever happened in 2023 because it was a more ocean-driven process. And so was the ensemble spread wider? Like was there less agreement?
There was a lot more spread in the 2023 values, but we actually did predict when we calibrated to it, we did predict it.
Yes, but I was just wondering if you could game that a bit to find years where maybe the ensemble spread was really wide for some inexplicable reason previously and say, well, maybe that was one of these years.
We've looked at those 73 years that capture values as low as the winter one, and we learned quite a bit. That's something that Nico's been doing as well, and I didn't have time to put it in this talk. It's also in that chapter I'm going to be reading, the Playing Back to Auckland. But what's influencing those really weird years, and what can we learn in comparison to this recent years? So similar to what you're asking, absolutely. As imperfect as it is, there's lots that you can still use this for to learn about and understand more about the processes in different ways that different things come into play and go out of play in through time.
Well, thanks, Ryan. Well, we've had a good discussion here, and is it just to check on Zoom if there's any questions, or does anyone would like to chip in? Or maybe